Several of these problems are of a procedure that I just alluded to in the lecture, of the method of initial rates. And the method of initial rates actually has several experiments, at least two, separate experiments that you perform on a given reaction. In this case, the reaction is here. And we focus on, for initial rates, we focus on reactants only, because we set the reactions up in such a way that there are no products. Because what happens is, as you start to build up product, you get reverse reaction. And that interferes with the determination of the rate of this part of the reaction. So that's why they call it initial rates. It happens at time zero, essentially. So we look at only these three. Like there's the protons, there's the oxalate, and there's the manganate. Okay, so what we do is we set up the experiment. We set up the experiment so that we can compare two of them. And we have concentrations here, and this is in molarity. Concentrations here, and then the rate of the reaction at the very beginning. And it doesn't matter what you're measuring here. You can measure right here, you can measure the appearance of one of these, or you can measure the disappearance of one of those. It really doesn't matter. But you set it up so that the concentrations, say you're comparing this one to the next one, and the next one, these two are the same, that one's different. And then the next one, these two are the same, these two are the same, these two are different. Since we've got three, we need another one that can be compared to this one. So these two are different, and these are the same. That's important to do the method that I'm going to show you. Okay. So remember how we write the rate law. Right, the rate. Well, if it was one component, we would say we would have a K, and then we would have the concentration of whatever component to some power. And this is the order of that reactant. Since there's only one of them, that's also the order of the reaction. If we have more than one, that would be the order of this reactant, and the order of the reaction would be N plus N. Okay, just as a review. Okay, so when we write, I don't think I'm going to have a whole lot of board. I might have to write over here. I'll set up the initial rate equation, because that's the question. What's the rate equation for this reaction? Okay, the rate equation then would be MnO4 minus to some power, and then the oxalate, oxalic acid actually, and then the last one, Mn, what are we going to call it? I don't want to say O, that looks too much like a zero. MnL. Let's write that. Picking it up, just barely. Okay, so we have it set up, and what we need is, actually, I left out. Okay. These values here, to answer the question, it doesn't want us to do K. It just wants the order of each of the reactants. Okay? So now, how do we get that information? We ratio. We ratio any two of the reactants where one is different. So if we say the rate, let's get these numbers. So this is experiment Roman numeral 1, 2, 3, and 4. All right, so what we're going to do is we're going to ratio, in order to find the first one, it changes here, but it doesn't change for these guys. Okay, so we're going to ratio, let's make the biggest on top. So we're going to ratio 2 to 1. Okay, and we're going to put in this information on the top here. So this would be actually, what's the rate for 2? 8 times 10 to the minus 4. Ratio for 1 is 2 times 10 to the minus 4. And then what is this one equal to? Well, it's equal to this one times the concentration of this one, 2 times 10 to the minus 3 to the m power. And the bottom one is the same K, because K is a constant. Yeah, so it's the same K for both of them. But for this one, it's 1 times 10 to the minus 33 to the same power, same order. The others, this one and this one, are going to be the same values, so they cancel. So they're gone. So all we have now is this one, well, that was gone too. So now we have this one, 8 to the 10 to the minus 4, divided by 2 times 10 to the minus 4 is 4. So that's 4. Is equal to what? Well, remember your powers, A to the m power divided by b to the m power is A divided by b, both to the m power. So this would be 2 times 10 to the minus 3 divided by 1 times 10 to the minus 3 to the m power. Okay, that's a legal mathematical process. But this is 2, right? That's equal to the m power. So what does the m have to be? The m has to be equal to 2. So now we know what this one is. Okay, we just do that for each one of them. Okay, so I can leave that one and that one. And now let's move to this one. So we're actually going to have numbers in this one, and these are going to cancel. So these are going to be identical. These two are going to be identical. This one's going to change. So we need one where it changes from this to this, but in the process, these two have to be the same. 2 and 3 would be good. So we'll put 3 on top since it's bigger. So 3 would be 1 times 10 to the minus 3 would be the rate. 1.6, excuse me. 1.6 times 10 to the minus 3 and 8 times 10 to the minus 4 on the bottom. So it's, this one is 2 times 10 to the minus 3. 1 times 10 to the minus 3. There we go. Okay, so now we know that it's, well, we need to change this one to minus 4. That makes it 16. Right? So now this one is 2 equals. This one is 1 times 10 to the minus 3 over 2 times 10 to the minus 3 to n. Oh, excuse me. I put that backwards.
Yeah, but 1 times 10 to the minus 3, 2 times 10 to the minus 3 is flipped.
There should be 2. That's 1. Yeah, that makes sense. Now that's 2 to the n power. So n has to be equal to 1. Okay. Now we do the last one. Okay.
How was that equal to 1 when the last one was equal? Oh, because the last one was 4.
Yes. 2 to the first power is 2. Okay, so this one's going to cancel out and leave this one. So which one does this one change? How about these two? 4 and 3. So the rate for 4 is 1.6 times 10 to the minus 3. And 1.6 times 10 to the minus 3 is the other one. I think we know where this one's going. So this is going to be 2 on top and 1. So this is 1 is equal to 2 to the L. L has to be equal to 0. Okay. So that was 0. Okay. Now, when we write this equation, that term drops out because everything to the 0 is 1. So we really only have these two. Rate equals K times that one to the second and that one to the first. So it would be second, first. That's it. You don't even put these in here. Okay. The question doesn't ask us for K, but how would we find K? It's really pretty simple, actually. There's our equation. So now that we've got our equation, we don't need to put that in there. We would just pick one of these and say, what's the rate? Say 2. 8 times 10 to the minus 4 equals K times 2 times 10 to the minus 3 squared, and then, and 1 times 10 to the minus 3, the first power, and solve for K. And you should get the same value no matter which one of these you use. Or if you think there might be some experimental error, just do all 4 of them and then average them. Okay, so that took a while. But it's the same method for everyone. Initial rates, always use that method. Okay, let's see, that's 2, 3, there we go. Except I got some ghosts left behind. The rate expression for a particular reaction is rate equals, for my benefit as much as any, B squared. If the initial constant, yeah, is that right? Oh, thank you. There we go. Now it's kosher. If the initial concentration of B is increased from 0.1 molar to 0.3 molar, so we triple the concentration, the initial rate will increase by which factor? Well, if we triple this one and square it, 3 times 3 is 9, right? So all things being equal except for this one, the rate should be times 9. Okay.
The only part that confused me on that was where that means B had value of, if it was 1 before and then you squared it, right? Or even if you didn't square it, if it was just 1, it says how much did it increase by? Which would have made me think it wouldn't be 9, it would either be 12 if it was 3 originally, or it would be, I don't know, the other answer would be out there. So I guess.
You're saying it increases by 0.2?
Yeah, well,
Why don't we square 0.2?
I get where we tripled it, but for it to increase by 9, that means the original value had to be, what was the original value of B is basically what I'm saying.
Oh, what was the original rate?
Yeah.
Doesn't matter.
Okay, so that's.
Whatever it is, it's 9 times now.
Okay.
It could be a different rate because it's based upon the first order of this one and the second order of that one. The rate could be almost anything. It depends on what these concentrations are and what K is for the actual rate. But whatever it is, it'll be 9 times greater if we triple this one.
Gotcha.
4. For which order of reaction is the half-life of the reaction proportional to 1 over K? K is the rate constant. Okay. What's the half-life for, let's see, 0 order, first order, second order? Okay. What's the half-life for each one of these? Okay. You remember? The easiest one to remember is this one. Right? Okay. What about the others? You remember those? I don't even know if I can remember those. Okay. This one is A0 over 2K. That makes this one, I think it's 1 over, yeah. It's 1 over K times. That makes sense. Because this one is a log transformation, this one's raw data, and this one is reciprocal data. So that puts this one in the down here. Okay, so to answer the question, which ones of these are proportional to 1 over K? They're all proportional to 1 over K. The inverse of K is proportional to each one of them. Now, I didn't show you how these were derived. I've since modified the slide, I think, to put those derivations in there. But they're not important if you remember these. But it's fairly simple. You just start with your integrated rate law. And you say, T, the 1/2 time. How long does it take for half to disappear? And you say that this one divided by the initial is equal to 1/2 of the initial. That ratio is 1/2 of the initial. And then you can solve and resubstitute into the equation and solve for the time. You can't use the differential rate law because it has no time term in it. Okay. Let's see. 4? No, we did 4. 5. Scroll up some. Okay. If the reaction 2 hydrogen iodide yields hydrogen plus iodide is second order, which of the following will yield a linear plot? If it's second order, we know that the concentration versus time, let's see, time in this scale, concentration of HI will give you a curve, right? And natural log of HI, this is first order. Let's do it this way. This is 0 order. This is first order. And this is second order. This one's a curve. This one's straight. If it's second order, that plot will be straight. Time against inverse will be straight. So if we take the inverse and plot it against time, you get a straight line. In fact, that's how you tell which is which. You just set it up in your Excel spreadsheet, your data set here, tell it to do the natural log in this one, tell it to do the inverse in that one, and then set up a, what do they call them in Excel? Charts. Chart this one, chart that one, see which one's straight. Okay. More scrolling. Let's do that. Then I can page and get to the next one. Which step is rate determining out of these two? So now we're talking about mechanisms. So these are elementary steps in a mechanism for that reaction. So if we go from here to here is the overall reaction, but it occurs in two steps. So we take one of these A2s plus a B2 and make an R plus a C. So there's one of your C's and one of your A's used, and there's your B. And this intermediate then reacts with the second A2 and makes the other C. That's your mechanism. The question is, which step determines the rate?
Step one is R.
The slowest one, yeah, right? This one's very slow and that one's slow, but the slowest one determines the rate. This one right here. And as it turns out, we can write the rate equation from that balanced step because the slowest one is the rate determining step. So in this case, for elementary steps, we can use the coefficients to tell us what the power is, what the order is for each of the reactants. Okay, so that's why the answer is B. The slowest step is the rate determining step. Okay, this reaction, 2NO plus O2 yields 2NO2, obeys this rate law. So oxygen, the decrease of oxygen, that's what the negative is for. The decreased change in oxygen is equal to some K value times NO to the second power times O to the first power. So it's first order for oxygen, second order for NO. So which of the following mechanisms will satisfy this experimentally determined? What's the first condition for a mechanism? You have to be able to add up the steps and get this equation. Okay, that's first. So we can eliminate, hopefully, we can eliminate some of these by just checking it out. Okay, there's two NOs. There's an NO. There's two NOs. Okay, that one's good. This is an intermediate, so it's used up. It produced here and used up here. One oxygen yields 2 NO2. So this one meets the first condition. Add up the elementaries. How about this one? There's one NO and one O2. Makes an intermediate, and then the intermediate adds to the second NO and makes 2 NO2s. That one matches. In this one, 2 NOs make N2O2, and then the N2O2 decomposes to NO2 plus O. So this one never enters into the react. Oh, wait a minute, I skipped this step. Excuse me. O2.
There's O2. That's just two of those.
Yeah, but this one's on the product side and that one's on the reactant side, so they cancel each other out. Huh?
They're on the same side because it continues on it.
No. These are separate steps.
Okay.
Yeah. So this one can't be. Right? There's no O2 in there, and those O's cancel each other out. Yeah. So we can eliminate C. And then this one,
There's too many others in that one.
yeah, O2 plus O2 yields O2 plus O2. That one can't be. That was stupid. So it's one of these. It's either A or B. Okay, now that we've got that part figured, well, it's possible that it's none of these. But the next step is, the rate determining step is the slowest step. So we have to use this one for that mechanism and this one from that mechanism to start with. So the first one would be rate equals some K. Let me see. I do need my cheat sheet now. Keep me from fumbling around. On page. Okay. Okay. So this one, the slow step would be determined by that. And since there are two of them, it has to be squared. So we can use the coefficient. There are two NOs here. We can square it. Let's see. Okay. But that doesn't agree with this one, does it? Where's the O? There's no O in there. Based on the slow step, there's no oxygen in that one. So by process of elimination, it should be B. So if we write B out, B would be the slow step is the rate determining step. So it would be NO3 first power and NO first power. There we go. But that doesn't agree with it either. In fact, there's no NO3 here or here. So what we have to do is say, all right, this is a fast equilibrium, which means the forward rate, and we could say this is K sub F and this is K sub R for forward and reverse. Okay, so the forward reaction would be so K forward is equal to NO and O2. They're both to the first power, but that's also equal to the reverse reaction, which would be, and this is a K, KF, and then K reverse times the NO3, NO3. I think I did that right. Yeah. Okay. So now, can we solve that equation and resubstitute it? We need to get rid of this one right here. So let's solve for this one. NO3 is equal to, take this one over here and put it underneath. KF, this is KR. These stay on top just like before. 2. Okay. Now we can substitute this group in here. Right? Yeah, we can substitute it in here. So now the rate is K, and then NO3 is KF, oops, okay, F times NO times O2 divided by K sub R. And then that's all times NO. Picking that up. Give it a little bit more. There we go. Okay, now we can simplify. These are all constants. Right, so they're the new constant. Combined constant. And this is NO times NO squared times O2. So there it is. That one does agree, the B. That's a lot of work. But we went through a process of elimination to simplify it. It was down to 2. And actually, if you're trying to get through a test in a reasonable amount of time, we would have determined by process of elimination, that's the only one it could be. Well, no, we didn't. Sorry. None of these. All right, so we had to verify that that was correct. Okay. Yeah, we need that diagram. Use the potential energy diagram shown to answer the following questions. All right. So we can get 8 in there. So we're saying, yeah,
It's easy.
this is a potential energy diagram. So right, this is energy, and this is progress. So the reaction is proceeding from left to right. Which letter shows the activation energy without the catalyst? So this is the reactants, and they've got to get up to a certain energy in order to go the other side, activation energy. So yeah, A is the right one for that.
It's easy too.
Which letter shows the activation energy using a catalyst? Right, there's the catalyst curve. E is the energy. Yep. What are these other guys? Do they even matter? How about this one?
It's like whenever it's finished, then.
Yeah, that's the change in energy. We call it enthalpy. So is this an exothermic or an endothermic?
And it's out. Endothermic.
Yeah, uh-huh. You got, you stored up some energy in the products over here. So you lost some energy in the process.
Yeah, but you pick some.
If it went back the other direction, that would be exothermic. And the rest of them, this is like total energy, and this is total energy of the reactants, total energy of the activated complex. They're thrown in there to confuse you.
Last week's what made me know the answers to that one, whenever we went over the graphs on that.
Oh, yeah, yeah. Okay. Scroll this. So be sure and stop me if any of this, well, you have, so I'm sure you will. Okay, this reaction is hydrogen peroxide makes water and oxygen. And this is a proposed mechanism. Actually, it says this is the mechanism. So in this case, this is the reaction, right? Reactants make products. So the products spit out this side, well, on this side too. There's a product, there's a product, there's a product. There's a reactant, there's one of them, there's the other one. It doesn't say which one's faster. Doesn't matter in this case because we're just answering the question, which one is the catalyst? The catalyst is always a reactant that comes out on the product side of the final elementary step unchanged. So this one goes in, it comes out here. That's a catalyst. In this case, it was a homogeneous catalyst because it's in the same phase as everything else. It's aqueous. That's the one you do if you want to make a volcano with hydrogen peroxide. Take potassium iodide. Yeah.
So it has to be the last part of the,
Yeah, it goes in at the beginning and it comes out at the end.
and that's because it is the very last thing there, right? 'Cause that's why H2O doesn't work, since it also comes out as a product.
It's H2O too.
Yeah,
Ah, okay.
there's a subtle difference there.
Yeah.
Yeah. Now, if it makes something here, on the product side here, and it's consumed over here, that's an intermediate. Right? And for all intents and purposes, you don't even know it's there. You can't measure it. Right? It's proposed. Okay, so that's why the answer is B. Go ahead, scroll. We don't need that one. But this one. Take a look at 12. Consider the reaction: 2 ozones make 3 oxygens. And this is the following mechanism. So the ozone decomposes into diatomic oxygen and a free radical. That's what that is. They don't show you the unpaired electron, but this one does have unpaired electrons. And then we take another ozone and react it with that free radical, and that makes 2 more oxygens. So we have 1 oxygen here, 2 oxygens there. And this one is an intermediate that's consumed. And these are 2 reactants. So this one adds up to that mechanism. I mean, this mechanism adds up to that overall reaction. If we assume the second step of the reaction is the rate determining step, and the first step is fast equilibrium, well, that's kind of a giveaway right there. It's a double bar error. This one's the slow one, the rate determining step. Which of the following rate laws is predicted by this mechanism? Okay, so here again, we got to start with this one. And our rate has to be O3 to the first power and O to the first power. We got my K again. Now, for the same reason, we've got an O here, and we've only got one O3. Well, we've got O3 in there, and the overall reaction doesn't matter. So we've got to find a way to substitute in for that O. The fast equilibrium says that the rate of this direction equals the rate of that direction. So the forward reaction rate is K forward reaction times forward reaction is O3 to the first power. And that's equal to the reverse reaction. But it is O2 times O. Okay. Now, since we have to get rid of, this one because it's an intermediate. So we got to solve this one for the O. So that puts these over on that side. KFO3 divided by KRO2. Go. Talking to me. Then we can substitute this one back in here. And that means the rate is equal to KO3, and then whatever O is equal to, which is KF times O3 divided by KR times O2. Right? Be sure I get that in the right way. This O, it's that one over there. Yes. This one comes up here like that. Yep. So these can be combined into a single K. And then O3 times O3 squared, and this one's in the denominator. So it's going to be an O2 to the minus 1. And that's C. Okay. Now, we've only studied whole number, 0 first and second order reactions. But the fact of the matter is, the order can be anything. It doesn't even have to be whole numbers. And you'll find that out when we do our lab. Well, when you work the numbers from the lab. Okay. Well, yeah. This one's not too difficult. Oh, okay. I'll stay over here. The following equation refers to 2a squared plus 2a sub 2 plus b sub 2 yields 2c. And the following mechanism is proposed. According to the collision theory, the activated complex that forms in step 1 could have which of the following structures?
R cancel out, C cancel out.
Well, we're looking at the activated complex for step 1. So you don't even have to look at step 2. The activated complex, because this is the rate determining step, we want to get A2 plus B2 to some form of activated complex. I mean, it's even in here. It doesn't even make it to that yet. Yeah. Okay, so what do these look like? This is A bound with A, and this is B bound with B. Okay, so an activated complex, which would be the most likely? Well, you're not going to have an R, because that comes out the other end. It's in here somewhere, so R's out. A and B could be like that. That's possible. So let me scroll to see so the rest of them and see if they make any better sense. There's B, I'll leave B there. C, and the way you have to look at this is B belongs to this, C belongs to that. It's an artifact of Microsoft Word, because this is the baseline for everything. C still has R in it, and D has R in it, and A has C in it, which is a product. So it can't be any of those. It has to be this one. That's the only possibility. D, 14, excuse me. Which of the following statements about enzymes is incorrect? So are all of them correct? We'll see. They are proteins that catalyze specific biological reactions. Yeah, that's true. Okay, this one checks out. Several hundred are now known. Well, actually, there's more than that. A lot more than that. But when this review document was created, that was true. I don't know, it's probably in thousands by now. Molecules they react with are called substrates. That's true also. They're equal to inorganic catalysts in efficiency. Actually, they're exceedingly more efficient than inorganic catalysts. Much, much more efficient. So D is the incorrect one. In fact, efficiency is not the only thing that they're good at. They're also extremely good at driving a reaction in one direction. And in fact, more often than not, there are some exceptions. More often than not, if a cell wants the reaction to go in the reverse direction, it needs a different enzyme. So I have like this and that. you'll have one enzyme here, and you'll have one enzyme there. But there are a couple of annoying exceptions to that rule. So there are a couple of enzymes that tend to go both directions just as easy. So the cells have a workaround, and it depends. There are basically three types of plants, green plants, that is. There are the C3 plants, the C4 plants, and the CAM plants. And the C3s are cool climate plants, because the cooler climate means that the reverse reaction is not so much a problem. But in the warm season, in the warmer regions where you have more C4s, the reverse reaction becomes a real problem. So their solution is, once you make the 3-carbon compound as your first product from photosynthesis, you immediately convert it to C4s, so it won't be able to go backwards. And then the CAM plants, they send their products into these C3 products into separate vesicles in the cell. They isolate it physically. And then when the sun goes down, they take them and carry on with the what they call the dark reactions. All right. Let's see. Nope, skip that. Probably because it's too involved. And we've already done one like it anyway. For reaction little a, big A yields products. A0 equals 4.2 molar. That's the beginning concentration of A. And the first two half-lives are 56 and 28 minutes. Calculate K. Okay. So it helps to extract information from this problem and build your table. So if we've got A in this column, concentration of A, and we've got time in this column, at time 0, we're saying the concentration is 4.2 molar. Okay. Then the first two half-lives are 56 minutes. First half-life is 56 minutes. So from 0 to 56 is a half-life, which means half of that's left. Okay. The second half-life is 28 minutes, which means the actual time from the beginning was 1484, right? 84 minutes. And the amount will be 1.55, right? Carry the 1. Wait a minute, 4.5, right? No, that's right. 2.1 is 5. Correct?
I'm not good when it comes to math.
He's doing too. Yeah, that should be right. Check the notes. I don't have to go to my calculator. 16. 05, excuse me. Yeah, because when you carry 1, there shouldn't be anything else there. If I doubled that one, it'd be 2.65. Okay, so now that we've got this data up here, what's the K? Well, let's see. First two half-lives are 56 for calculate. Okay, they don't tell us whether it's 0, first, or second order. Right? Since they don't tell us, then we've got to eliminate by calculating the K for each one of these steps. If it's, depending on whether it's 0, first, or second order, if we calculate a K for this one, with our equation and one for that one with our equation, the K's should be equal. If they're not equal, then it's not second or first order. And we'll already have the K when we do that. So the zero order is what? Half-life equals K, excuse me, K's on the bottom. A 0 over 2K, is it? I think. Yep. Okay, so for the first one, half-life of 56 should be equal to this value, 4.2, is that right there, times 2K. So I'm going to have to use my calculator first. So we solve for K. Put K over here and 56 over there. And 4.2 divided by 2 and then divided by 56 is 3.75. Let's see, K equals 3.75 times 10 to the minus 2. Now for the other one, its half-life is 28. Right? And but that starts at 2.1 divided by 2K. So K is going to be 2.1 divided by 2 and then divided by 28. 3.75 times 10 to the minus 2. So that's it. But it can't be all three of them. It can only be one of them. So we did the zero order calculation and found that the K's were equal. So that means it is zero order and the K is 3.7 times 10 to the minus 2. And it should be 375. Actually, if we rounded it, it would be 3.8. So technically speaking, we could say none of these. Right? So if that happens, if this happens and you put down that and I mark it wrong, then call me on it. Because technically, if you show me your work, you say, okay, no, rounded it should be 3.8, so it's none of these. Okay. We won't even bother with the others, but you do the same thing. You set up first order and check your K's for the first order, check them for the second order. And they should be wrong in this case, not be the right ones. Oh, I see what I did in when I actually when I did the work problems. I determined what the order was first, and then did the calculation. But this is simpler. You just do them until you find the right one. So I probably need to modify that. Because you're not going to have you can tell from this printout that I did that in Excel. And you're not going to have Excel on an exam. Okay, let's see. Are we going to do 17 also? Yeah, 17. All right. So for this reaction, dinitrogen pentoxide yields nitrogen dioxide plus oxygen. The following data were collected. So at time 0, the concentration was this of N2O5. And then it's gradually decreasing. Okay, now what are we looking for? The initial rate of production of NO2 for this reaction is approximately what? So the initial rate production of NO2. Let's see. In order to do that, is the initial rate. I'm looking to see if there's a simpler way than to do it this way. If this type of problem for homework, you know, review document, this is fine because you've got resources where you can actually determine whether it's 0, first or second order and go from there. But on an exam, it needs to be simplified so that you don't need that information. All right. No, I'd have to skip this one. Because I determined from my Excel program, this is a first order equation. So I would tell you this is first order. Say, there's the data and it's first order. Okay. Now that we know it's first order, then we know that the equation would be natural log of N205 equals K, so minus K. Yeah, minus K times T plus the natural log of N205 at the beginning. Okay, now we can get at the rate constant. Right. We should be able to do the rate constant. All we have to do is pick values. Okay. So I think in that problem I worked out, I said, okay, after 70 minutes, so time is 70. And then the natural log of the beginning concentration was 1.24 times 10 to the minus 2 molar. And then this one is the natural log of at time 7, 0.15 times 10 to the minus 2. And then solve for K. Okay, and K turns out to be 3.02 times 10 to the minus 2. 3.02 times 10 to the minus 2. After you solve all that equation. Now that we know what K is, we can say the rate is equal to 3.02 times 10 to the minus 2 times N205 to the first order. Okay, and the rate is disappearance of NO2. No, the appearance of NO2, excuse me. The appearance of NO2. Yeah, initial production of NO2. So the rate of production of NO2 with change of time is equal to that. Okay. And more of the question. Oh, so the initial rate is what is the rate right here? So that concentration goes in there. This one becomes 1.24 times 10 to the minus 2 to the first power times this, and that's the initial rate of production of NO2. Right? Now, why did I put that step in there? Maybe I'm, okay, hold on a second. No. That's not right. This is based upon N205 only. So this one times that one gives you the rate of consumption of this one. Okay, have I confused you? This value here has to correlate with that value. Right? We can't make the jump to NO2 yet. But once we find out what this rate is, and that rate is, let's see, 3.74 times 10 to the minus 4. Molarity per, what is it? Minute. And this is that one. But as this one disappears at that rate, for every 2 of those, you get 4 of these. So the actual rate of production of NO2 is twice that. Okay. We're good. He's still digesting. So that's why, let's see, 7.4 times 10 minus 4. Here it is. That was probably one of the worst ones to digest. Okay, 17. We do it. 17. Here we go. Oh, the question below. So we don't need that part. We just need this part. 17. The initial rate of production of NO2 for this reaction. Oh, no, we already did that one. We do need to go to the next one. Question below refers to the following information. The rate constant K for the reaction shown below is 2.6 times 10 to the minus 8. So K for this reaction is given as 2.6 times 10 to the minus 8 liters per mole second. That tells me it's probably inverse. So I bet this is second order. 18. Let me read through the rest of the question. K for the reaction, when the reaction proceeds at 300 K. So this is for 300 K temperature. Oh, I see what we're doing. The activation energy is 98,000 joules per mole. Okay. If the temperature changed to 310, the rate constant K will change. Yes, it will. The ratio of K at 310 to K at 300 is closest to what whole number? Okay. So you need to look in the useful information and find the modified, I'm searching for the right word. What's the guy's name? Arrhenius. The integrated Arrhenius equation. And it will be this one. The natural log of K at the high temperature, so that would be 310 over K at the lower temperature is equal to activation energy divided by the rate constant times 1 over T at 300 minus 1 over T. Well, actually, that's it. What am I saying? This is 300 divided by 310. Okay. The lower minus the higher. Let's see, is there a There's supposed to be a negative in there. Okay, I'm just checking. Yeah, okay. So, this is gonna be 98,000. And this is gonna be 8.314. This K, well, actually, that's all we need. Because it asks, what's the ratio of this one to this one? Right, so we don't need to put anything in there. We just need to solve this part of it. So what's the inverse of 300 minus the inverse of 310? And that's 1.07527 times 10 to the minus 4. Okay. And then this one would be divided by 8.314 times 98,000. And that is 1.267 is equal to the log of that ratio. So the ratio itself is actually the anti-log of this value. Yeah, I did write that too well. 7. There we go. So we just need to take the anti-log of this value. Here it is. 3.55. So it's nearest to the whole number, 4. Right. Yep, there we go. Did I lose anybody? We're good.
It's ironic. See a little circle that's already been around 4. Whenever you just go down, it's about perfect.
Oh, that was accidental one. There we go. Okay, that was 18. Let's get 19. 20. Okay.
After little accidents, that's what John Ross used to say.
Accident.
That's what you say, and after little accident or accident.
First order decomposition of H2O2 at minus 30 occurs with a half-life of 42 seconds. First order decomposition. So we've got concentration of H2O2, the time, and the first half-life, T0, is 42 seconds. What else are we given? Well, it's at minus 30 degrees C. What will be the residual concentration of 10.2 millimolar after 3 minutes? So we're starting off at 10.2 molar. And we want to go down to 3 minutes. So how many seconds is 3 minutes? 180? 180. So we're going down to 180 seconds. Okay. So if we're going to get actual concentration after so much time, we need the integrated rate law. So first order, T1 half equals 0.693 divided by K, correct? I think that's right. So first order, this 42 seconds is this one. And well, that means K equals 0.693 divided by 42. Right? 0.693, 42. So that's 1.65 times 10 to the minus 2 is K. And the first order law will be natural log of H2O2 is equal to minus 1.65 times 10 to the minus 2 T plus natural log of H2O2 0. So the question is, what will be the concentration of H2O2 after 3 minutes? So we know the initial is 10.2. We know this. And the time is going to be 180, which is equal to the natural log of that answer. So if we say 180 times this value, and then we say the natural log of this one, 10.2, and add it to that value, and that means the natural log of our answer is equal to 5.292. So we just need to take the anti-log of 5.292. And I get that doesn't look right. I did something wrong. Negative. Let's go back. 1.65 exponent to change the sign. And let's change the sign on that one. And then we'll take the 180 times that. Okay. Now we're going to 10.2, take the natural log of that, add it together with this one. Okay. So this is minus 0.6476. Take the anti-log of that is 0.523. 0.523 molar. There it is. B. How did I know I got the wrong answer? Because the answer I did it the first way was bigger than the initial concentration. That's a dead giveaway. I think that's the last one, isn't it? Kinetics is not the most fun for most people, including me. But a good understanding of kinetics is essential to go to the next step, equilibrium.